I'm here to talk about high system code security and low overhead. And this is joint work with my colleague, Volodymyr Kuznetsov, and our advisor, George Candia at EPFL, as well as Johannes Kinder from Royal Holloway University of London. And we are interested in high system code security because we use a lot of systems code and it's dangerous. For example, a single memory access that goes wrong can have dramatic consequences, like in the case of OpenSSL about a year ago. And this was a single memory access, but there are literally tens of thousands of memory accesses in OpenSSL. And we've heard about this buffer overflow way too much. We would like to move to more interesting research like the SSL research from yesterday. So is there a way to, once and for all, get rid of all these problems with memory accesses and other low-level issues? And we are advocating a way to solve these problems using sanity checks. These are runtime checks, and I'll give you an example. If you have here a pointer dereference, you could protect this dereference by adding a check just before the dereference to verify that the address is valid. And if it happens to be out of bounds, you would report the error and abort the program. So note that aborting the program is, in this case, the only safe thing that you can do, because if you were to continue, arbitrary bad things can happen. Now, we like sanity checks because they can be added automatically at compilation time. So there are a number of good tools like Address Sanitizer that would generate checks like you see on the screen. And they also don't need the source code to be modified in any way. There's just one issue with sanity checks, which is that our system code is very performance sensitive. So people usually are not willing to pay a high overhead for these checks. And the table here shows a number of popular tools to generate sanity checks together with their overhead. And you can see that they all add 70% or more to the runtime of your software. So sanity checks are a bit like plate armor. It provides really strong protection, but it's also heavy. This is actually why people are using sanity checks quite extensively during testing and development, but they turn them off in production builds. Now the question of our work is, can we take away the overhead of sanity checks in order to enable people to use them in production? And surprisingly, the answer is yes. And here is why. Our insight is that all these sanity checks are not all equal. In fact, most of the overhead comes from only a few checks. These are checks that are in hot parts of your program, thus they are executed very often and are expensive. On the other hand, most of the protection that users get comes from checks that are cheap because they are in cold parts of the program. This insight is the rock on which we build our approach. So our approach starts with the user and allows the user to choose their overhead budget, which is the amount of runtime they are willing to invest into checks that protect them. This is usually a low number, like 5%. But then we build a system that automatically identifies the sanity checks in software and measures the cost of every single check, and also then selects just as many checks as possible while respecting the budget that the user specified. We call our approach ASAP because it generates software that's as safe as possible for a given overhead budget. Now, the result of using ASAP is rather surprising. We performed some measurements on a number of benchmarks from the SPEC and Phoronix benchmark suits, and we measured both the overhead of instrumentation as well as the amount of protection that you can get. We measured the fraction of critical operations in a program that are protected by checks and call this the sanity level. When you do this, you obtain a curve that's very skewed, like here. This means that there's indeed a large fraction of the protection that is very cheap and comes at almost no performance cost. On the other hand, if users want 100% protection, they also have to enable a few checks that are very expensive and cause overhead to quickly grow. Using ASAP, a user could now choose any point on this performance and security trade-off. And for example, a user on a 5% budget can obtain about 87% of the protection. I've gave you the principle behind ASAP, and I am next going to present our design and discuss some of the key algorithms that make ASAP work. I will also show more results in more detail. Now, we designed ASAP to be built into the compiler. In our case, it's implemented using the LLVM compiler framework. This choice makes ASAP fairly easy to use. Users essentially need to set their C compiler and C flags environment variables, and everything else happens automatically. We also carefully built ASAP so that it's compatible with many different tools that add sanity checks, and also things like parallel compilation or shared libraries. ASAP has three main components, namely to identify sanity checks in programs, a profiler to measure the check's cost, and also an optimizer to select the optimal set of checks for a given budget. A user uses ASAP just like a regular compiler that generates a binary that's protected using checks. ASAP would, in addition, store the intermediate outputs of the compiler. In our case, this is files in the LLVM intermediate representation. It uses this output to generate variants of the program. So in a second step, the ASAP profiler generates an executable that contains extra code to measure performance. Users can run this executable against a workload of their choice. And when they do, it computes the cost of each of the sanity checks. ASAP uses this cost as well as the user-specified budget in order to generate an optimized program that contains just those checks that provide most protection while fitting in the budget. We are next going to look at some of the key algorithms in ASAP. ASAP is this black box that generates fast protected programs, and it contains a number of important parts. I'll have to refer you to the paper for many of these, for example, on how ASAP identifies checks or how to select a good profiling workload. I'm going to just focus on two of the points here, namely how ASAP measures the cost of checks and how it quantifies protection. In other words, can users trust ASAP to really select the checks that consume the least amount of CPU cycles? And also, if ASAP gives you a certain protection level, what does this really mean? Let's discuss how ASAP measures the cost of checks. This is again the sanity check example from the beginning of my presentation. In order to measure its cost, ASAP would, in a first step, insert profiling counters into the program. This happens during compilation and uses the same existing profiling infrastructure that's present inside LLVM. ASAP adds one counter to every basic block of the program, and these get incremented while the program runs. And thanks to that, it allows ASAP to see exactly how often every instruction in the program has been executed. ASAP also identifies the instructions that belong to sanity check, and it uses a static cost model to essentially convert instructions into CPU cycles. This is also the same model that compilers traditionally use for optimizations. With all this data, ASAP can now compute the cost for every check. It multiplies the number of times an instruction is executed with the number of cycles and such an execution takes. And it sums up these numbers over all the instructions in a sanity check. This gives a precise cost measured in CPU cycles. And in practice, we found that this works very well to distinguish both the checks that are cheap and the checks that are expensive. So next, I want to talk about security. If ASAP gives you a certain protection level. What does this really mean for your security? Now, ASAP quantifies the protection that it gives you using the sanity level. This is the fraction of the critical operations in the program that are protected using a check. However, what we would rather like to know from a management perspective is the effective protection level in terms of bugs or vulnerabilities or security incidents that we are now protected against. Our methodology to relate these two quantities is to look at existing known bugs and vulnerabilities and measure how many of them are effectively prevented at a given sanity level. Our first experiment to do so, in our first experiment, we looked at the source code of the Python interpreter. And we defined as a bug each line of code that has changed between the versions 2.71 and 2.78. So no new features have been added between these versions. So each line that changed was previously buggy. We then measure, for a given sanity level, how many of these buggy lines are protected using sanity checks. Here are the results. For example, you can see that at a sanity level of 87%, effectively 91% of the bugs are protected. More generally, the red line that shows the effective protection is always above the diagonal. So this means that the sanity level is a lower bound on the effective protection that users can get. We also performed more experiments where we looked at known bugs. We looked at bugs in Python or OpenSSL, but also in scientific benchmarks like the RIPE buffer overflow benchmarks. We found a number of locations where the buffer overflows occurred, and in all those locations that we looked at, they were in cold code where they can be protected by cheap checks. We also looked at vulnerabilities from the CVE database. So we systematically analyzed all the memory safety vulnerabilities from 2014, for which we could get the source code and a patch and the location of the error. There were 145 vulnerabilities that satisfied these criteria, and we found that 83% of these were located in cold code. Now, it's hard and probably dangerous to draw conclusions about security from these experiments, but all these experiments indicate that checks that are in cold code actually do provide real value for protection. Next, as promised, I'll show some more results about ASAP. On this graph here, you can see the overhead that we measured on the SPEC benchmarks when adding the sanity checks generated by Address Sanitizer tool. As you can see, Address Sanitizer has a rather high overhead. It's usually above 50% and sometimes even above 100%. Now, using ASAP, users could now reduce this overhead by choosing a slightly lower sanity level. So here, you can see the overhead for a sanity level of 95%. So all the red parts in this figure are CPU cycles that we save by reducing the protection by 5%. Users who want even lower overhead can reduce the protection level further. So here is the result for 90% sanity level. And here it is for a sanity level of 80%. Now, I would like to highlight two things. The first is that for some benchmarks, there is still residual overhead. And we found that this is actually overhead that is not due to checks, but due to other things that Address Sanitizer does, like changes to the memory allocator or effects on the instruction caches. Now, Address Sanitizer was not built with ASAP in mind, so we think that some of these causes for residual overhead could be addressed with the future instrumentation tools. For the other benchmarks, the overheads are now well within a range that people would be willing to pay during production. So we can conclude that ASAP effectively provides high protection at low overhead. I will conclude by saying that runtime checks are a great way to protect software. Their cost is high, but we found that the cost usually comes from just a few checks that are expensive. On the other hand, most of the protection comes from checks that are cheap. So we built ASAP, a tool that allows the user to specify how much overhead they're willing to pay and creates an executable that provides maximum protection for that overhead budget. With ASAP, protection no longer has a high cost. So I would encourage you to go to our website, download the open source version of ASAP, and try it out to protect your software. Thank you.
Okay, we have time for a few questions.
Venkat from UIC. I have a couple of questions. The first question is more of a clarification. I didn't quite catch whether the definition of sanity level is a static measure or is it a dynamic measure? Is it based on your profiles or is it based on some analysis that you do of the code?
Okay, so this is a static measure. Essentially, we look at the program, and in the program there are many instructions that are potentially dangerous, like memory access instructions, like loads. And all of these could be protected by a check if you use a systematic tool. And now we define as the sanity level the fraction of these checks that are effectively present in the optimized version that ASAP generates. Does that make sense?
Yes. My other question is, I'm somewhat surprised that you have not factored the influence of input on any of this, because there are essentially many checks that can be done on a program where the user input will not have any influence, and therefore so the real bugs that are exploitable are ones that can be influenced by user input. So, but I don't see that in your trade-offs. So.
Yes. So I think this is a great point. So what we do is we look at each check and we select them or not purely based on their cost. And what you're saying is that you could also select checks based on their merit or based on whether the operation that they protect has input-dependent data or so, right? Now, what we do is, we decide purely based on their cost, and we show in the graph about Python or so that this is actually a conservative assumption in some sense, in that checks that are cheap tend to have a slightly higher impact for protection than checks that are expensive.
But it is also somewhat counterintuitive to me if there are no. Maybe we can take this off.
Yeah, thank you. With pleasure. Yeah.
Hi there, Trent Jaeger, Penn State. Nice talk.
Thank you.
I wanted to explore this hot path, cold path thing a little bit. Mm-hmm. So the notion, I think we've also experienced that cold paths often are where the bugs are now, where the vulnerabilities are now. Mm-hmm. But I guess what I was wondering is, did you explore, it seems that on the hot paths, people might already have added sanity checks into the code manually on the hot paths in order to, defend things because they've already seen these paths be run several times and so forth. And so I was wondering if your analysis looked for existing sanity checks that were already in the code, and in some sense maybe, you might, improve or verify or replace the sanity checks that are there with better ones at very low cost in that sense. So I was just wondering if this intuition was consistent and if you had thought about looking at the existing checks.
Yeah, so there are a couple of elements to the answer. And the first is that, our tool does work with, for example, assertions that developers manually put in. It recognizes them just like any other type of sanity check. And also, users have some control over which parts of the program are hot and which are cold if they select their training workload accordingly. So we have quite a lot of information about that in the paper. For example, we explored what happens if users use their test suite as a profiling workload, because that would automatically stress the parts that are well tested more and remove more checks from the well tested parts.
Right.
Does that make sense?
So you were looking at the existing sanity checks?
Yes, we do. Yeah.
Thanks.
Please try to keep it short to stay on schedule.
Sure. So I guess address sanitizer's a debugging tool, and you're promoting this as a mitigation technique. I guess some previous talks we've seen have suggested that one has to be quite careful when designing mitigation techniques to be resistant to attacks. My take is that bounds checking and so on is a pretty sensible thing to do and helps both with debugging and with security, but have you spotted any differences between some of the more interesting and more adversarial-centered mitigation techniques and the kind of debugging techniques that are present in address sanitizer?
Mm-hmm. So yes, this is true, and I want to say that we actually did test our tool also with something like softbound, which is a more security-focused way to add bounds checks. And also in the CV study that we did, we looked at all these vulnerabilities, and we found that for about 4 out of 5, we could tell with some precision where the overflow would occur and what object this was, and whether it was an overflow that was just linear, which would be caught by something like address sanitizer, or whether it was a more complex thing. And we found that, yeah, in about 4 out of 5 cases, even unsound protection like address sanitizer would probably have helped.
Thanks.
Okay, let's thank the speaker.